The next question is, which competitive equilibrium will Anne and Ben end up at if they trade based on the original endowment? We can answer this question by approaching the problem from Anne's perspective, using her rule for optimal consumption, her budget constraint, and combining that with the expression that we've derived for the contract curve. So to get started, we'll remember that Anne's optimal choice rule will be such that her marginal rate of substitution is equal to the price ratio. Prices in this model are a bit arbitrary because we don't have any money. We simply exchange good X for good Y. And PX over PY then just represents the rate at which we exchange these goods. Therefore, we can assume that PX is equal to 1 without any loss in generality. So for Anne, her marginal rate of substitution was YA over XA, and that would be equal to 1 over PY. I'd like to solve this equation for PY because in a moment I will combine it with the budget constraint. So we've talked a little bit about resource constraints, but we haven't talked about budget constraints. In the budget constraint for Anne, we know that she has an initial endowment which represents her wealth, how much she has, that she can trade for what she wants. What we'll do is we'll set equal the value of her initial endowment to the value of her final competitive equilibrium endowment. So initially, Anne had 6 units of good X. The price of X has been assumed to be 1. And she had 2 units of Y. We'll plug in now PY as XA over YA. So this is the value of her initial endowment, omega A. This must be equal to her eventual consumption of XA times 1 and her eventual consumption of YA times the price of YA. So now what we have is an equation with just XA and YA. And what we'd like to do is simplify that equation and then combine it with our contract curve in order to solve for the competitive equilibrium values for XA and YA. All right, so I've got this canceling out. I've got 6 plus 2XA over YA equals 2XA. Recall that our contract curve was YA equals 12XA over 8 plus XA. You can see now how this is helpful because if I plug that into my simplified budget constraint, I now have a function of only XA that I can solve for our competitive equilibrium value. So I've got 6 plus 2XA times, now I've got 1 over YA, which will be the inverse of this equation for the contract curve. And XA's here cancel out. So I've still got something that's a little messy because I've got this 6, 2 divided by 12, it's 1 over 6 in the denominator. I think the easiest way to approach this issue is just to multiply everything by 6. So I've got 6 times 6 is 36. When I multiply by 6, that denominator goes away, and then this will be 12XA. So now I've got 36 plus 8 is 44 equals 12XA minus XA is 11XA. So XA will be equal to 4. And then I can plug that back in to get YA. 12 times 4 divided by 8 plus 4. So that is also going to be equal to 4. And then I can plug in further to my resource constraints to get the value of X and Y for consumer B, for Ben. So this is the competitive equilibrium point that we will reach if we begin at the initial endowment and just allow Anne and Ben to trade with each other. We can go back and show this on the graph, right? It's actually this point here along our contract curve. And if you plug in for prices, you'll see that PY was equal to 1. Of course, PX we assume to be 1. So we're trading these goods at a rate of 1 to 1 from our initial endowment point. And we end up here at this point for 4 for Anne and for 2 for Ben, which is a Pareto improvement from our initial endowment.